So let me talk a little bit about the famous Amore model. The u dt equals minus u plus the integral minus theta to infinity j of x minus y h of u of y t minus theta dy. So there's a couple of parameters in here. One is the shape of this, and and theta is the threshold, okay, above which you guys fire. So the idea of this model was Amore wanted to compute something that looks like a localized region which turns on, all right? So what does that look like? Here is x, there's 0. He's looking for something where some pile of neurons is turned on, okay? And by turned on, I mean above threshold, okay? So we'll call such a structure a bump. And the question is whether you can construct such a bump. Now this is on an infinite line, so you can move it anywhere you want, right? Because it's translation invariant, because this only depends on the difference between x and y. So we will center our bump at the origin, okay? And then ask whether we can construct such a bump. And then our usual question, whether it's stable. But I won't go through the stability argument because it involves formally differentiating this to get a delta function, and integrating delta function is hard, okay? So we won't do that, but I'll just, let me construct the bump, okay? So let's recall that j of x is some function that is symmetric about the origin. Maybe it looks like that. Maybe it looks like this. We're going to assume it looks like this, but we don't have to. But we're going to treat this generally, okay? In fact, you can get more interesting ones. People have considered ones that look like this, you know, with lots of wiggles, okay? But let's not go there yet. You'll see what the consequences of these wiggles are, okay? Or these dips like this, okay? They're kind of cool, all right? So let's see if we can find stationary solutions. U of x equals minus theta to infinity j of x minus y h of u of y minus theta dy, okay? So it's clear that all we have to worry about is minus a to a here in the integral, because that's the only place where this is above threshold. Remember, step function is 0. So this is equal to minus a to a, j of x minus y dy, right? Okay. And so I don't want to screw up the algebra on this. So let's define that. The antiderivative of this. So we can write okay. Now what we have, what is the unknown here now? A, right? The width of the bump. Everybody see that? Okay. What do we know about A? What defines A? What defines A? Exactly where it's equal to threshold, right? Because for x greater than a, it's below, and for x less than a, and between zero, here, it's above, okay? So, U of A theta has to be equal to u of a, right? Equals the integral minus a to a, j of a minus y dy. And that, make a change of variables, is just w of 2a. Right, where we've used w of x to be this. You can see that by making a change of variables. This is symmetric, so let y prime be a minus y, and then this becomes minus or 0 to 2a, okay? Got it? All right, so look, we've reduced the existence of this bump into a simple algebraic equation, theta equals w of 2a. So let's look at what w looks like. Oh, you might ask what happens at minus a. It's the same thing, okay? Because of the symmetry of this, right? What's w of x look like? Well, let's suppose this, let me have j1 and j2, okay? So I'll have w1 of x. What does that look like? It's the integral of this, 0 from y equals 0 up to x, right? So it looks like this. W of x looks like this, w1. Right? Buy that? Okay? Monotonically increasing because it's strictly positive. I'll assume it's integrable and all those things. What's W2 of x look like? Well, that starts to go up, right? And then we hit a rough patch with negative, and then we go back down. So we have a picture that looks like this. Okay, right? W2 of x. So we need theta equals w of 2a. Okay? So we just draw theta across here. If theta is too big, we'll never find a solution. Okay? And if theta is below 0, of course, we won't either. But there's a range of thetas in here where there's an intersection, and that's 2a. Okay? And that gives you the total width of the bump, because 2a is the width of the bump. So that tells you the bump width. In this case, if theta is really low, there's a little skinny bump. And if theta is intermediate, then there's 2a1, 2a2, a thin bump and a fat bump. All right? And this is sort of the PDE, infinite dimensional analog of a saddle node bifurcation. Remember those? Where you have two guys come together and annihilate. So here, there's two bumps, a little skinny bump and a big fat bump, and as we change theta, they come together and disappear. So it's natural to ask about the stability. Maybe I did do the stability. Let me see if I did the stability. Oh, okay. You know what? I'm going to try and do the stability. I hope I don't get stuck here, but I'm going to try and do the stability formally. Okay? But if it doesn't work out, the bottom line is skinny bumps are unstable. Okay? And fat bumps are stable. Okay? But let's do the formal stability. Okay? dv dt equals minus v plus the integral minus infinity to infinity j of x minus y delta of u of y minus theta v of y dy. All right? That's the formal equation. Do you see that? Right? Do you see why that is? Because the derivative of the step function is the delta function. Okay? And u of y is our bump that we've just computed. All right, now here's an old thing that you probably don't remember. Oh, if you take the delta function, or here, let me not do it this way. This is a very specific case. Let me recall this, okay? How many of you guys have seen have studied the theory of distributions at all? Oh, there's one. Right? Did you just raise your hand? Yeah. Theory of distributions is sort of the theory for delta functions and things like that. Double delta functions, delta function primes, and things like that. They're sort of not really functions, but you can define them in terms of integrals. All right? But let q of 0 be 0. Let q prime of 0 not be 0. Let q be differentiable. Okay? Right? Then the integral from minus infinity to infinity, delta of q of y, phi of y dy is equal to phi of 0 over absolute value q prime of 0. Okay? That's a result from the theory of distributions. Okay? The way to think about it is that if q is differentiable, then near y equals 0, it's like q prime of 0 times y, and then you make a change of variables. Okay? But you're going in one direction if it's positive, and the other if it's negative, so you have to change signs. Okay, so with that in mind, we can evaluate dv dt equals minus v plus j of x minus a times v of a over u prime of a plus j of x plus a v of minus a over u prime of a. U prime of minus a, but it's the same thing, right? Because it's symmetric. The absolute value is the same. You see that? Remember the bump? This slope and this slope are opposites, but they're equal in magnitude. Okay? Now, what do we know? We know u of x is equal to minus a to a of j of x minus y dy, right? So u prime of x is the integral minus a to a. Let's see. This is where let's see. I want to get rid of, let's see. Yeah. Okay, here we go. Let's let y prime equal x minus y, okay? dy prime equals minus dy. So u of x is the integral there we go. Right. This will be plus a, this will be minus a, but there's a minus sign, so I flip the integral. Okay? So, u prime of a is j of x plus, or u prime of x is j of x plus a minus j of x minus a. Right? By the fundamental theorem of calculus. And so u prime of a is j of 2a minus j of 0. There we go. That's very useful. Okay? Everybody good with that? Okay. All right, now we're almost done. Because we've done the hard part. We've evaluated that derivative, and I haven't screwed it up. So how do we solve this? This is a infinite dimensional equation. But we know that it's independent of time. So v of x t must be equal to psi of x e to the lambda t. Okay? If we plug that in, we get lambda psi of x equals minus psi of x plus j of x minus a psi of a over plus j of x plus a psi of minus a over u prime of a. Right? Everybody good with that? I haven't done anything too weird. Is everybody okay with this? Now, this looks like it's an infinite dimensional problem, but in fact, we don't care about anything except when x is a or minus a. So we have lambda psi of a equals minus psi of a plus j of 0 psi of a plus j of 2a psi of minus a over j of 0, j of 0 right? And lambda psi of minus a equals minus psi of minus a plus j of 2a psi of a, right? Put in x equals minus a, j is symmetric. So you get minus a, minus 2a, j is symmetric, so that's okay. So we've reduced it to a 2 by 2 matrix. All right? And what's the 2 by 2 matrix? It is minus 1 plus, let me call this quantity C, so I don't have to keep writing. Okay? Okay? Minus 1 plus right? And minus 1 plus j 0 over c and j of 2a over c. Right? Ah, well, this is our old friend, A, B, B, A. So the only possibility is the eigenvalues of this. I mean, it reduces to lambda is equal to this plus this, and this minus this. Right? Isn't that easy? So we've taken this, so lambda is equal to minus 1 plus j of 0 minus j of 2a over j of 0 minus j of 2a. Okay? And lambda equals minus 1 plus j of 0. That's the 1 minus 1 guy. And then there's the 1 plus 1, right? That was the corresponding to 1 minus 1, right? And then the other one's 1 plus 1. Okay? Absolute value. Okay, we're almost done. Now let's take a look at J again. Maybe it looks like that. Clearly, J of 0 is the biggest guy. Okay? So we can get rid of the absolute values. How many of you guys hate absolute values? Right? Raise your hand. Right? Right, they're a pain in the neck, right? Oh, is it positive or negative? Okay, this is so much easier when it's, well, that's equal to 0. Huh? Okay, now here's a big question. Why is there a 0 eigenvalue? You have a thought? Any thoughts on why there's a 0 eigenvalue? What was the first thing I told you about the bump? I told you I could slide it anywhere. That 0 is an instability. It's not an instability. It's the fact that I can slide that bump anywhere. That's the 0 eigenvalue. Remember, u dot equals 0. There's infinitely many constants. There's actually infinitely many bumps that I can move anywhere. So we don't worry about that one. Just like, yeah, if we don't worry about that one, that's our friend. Okay, we don't care. Okay, so, okay. What's this equal to? Well, this is equal to j of 2a minus j of 0 plus j of 0 plus j of 2a over j of 0 minus j of 2a. Right? Just put this, I put this over to here, put it under a common denominator. Okay? And what's that equal to? That's equal to j of 2a over j of 0, j of 2a. Okay? So that's the other eigenvalue. All right? Now you remember, we're almost done. We almost have the big result that we want. Okay, we're almost done. Okay? Remember, we had two w of x's. There's w1, and there was j1, w1, a, okay? And the other one was, or 2a, this was 2a, remember? 2a. The other one was j of x looked like this, and w of x looked like this, right? And there were two of them, 2a, 1, 2a, 2, okay? What's the eigenvalue? That's just j of 2a over this, right? J of 2a is there. It's positive, right? It's always positive for this guy. Unstable. How about this guy? J of 2a1 is before this guy reaches his negative part, right? So it's in here. So it's positive, unstable. J of 2a2 is in this region where he's negative, stable. Isn't that neat? Okay. There we go. So we've just shown that the thin bump is unstable and the fat bump is stable. okay? So in fact, the thin bump is kind of like a separatrix, but if you start with initial conditions that are above the thin bump, then it'll grow out to the fat bump. And if you start with initial conditions that are inside the skinny bump, it'll shrink back down to 0. So this is a bistable thing. There's either a zero state where nothing happens, and there's a stable bump. Okay? So that was sort of the model that Amari had for working memory. His stability was quite different. His stability analysis is very different. Okay? All right. So somebody forgot to set the time. So I don't know what the time is. Okay. They forgot to set the alarm because I looked. I said, "Oh man, that really went slow." I thought I was talking for at least like 20 minutes there, but it still says 1:25. It's all right. Hi, Mom. Don't they always do that, you know, in the stadiums or something? Okay. All right, now I want to talk about some fun stuff that is related to what I'm going to talk about on Sunday, okay? So you guys are going to have to do an experiment. It's a little bit painful, but, you know, science is painful, all right? So what you have to do is if you have glasses, you probably have to take your glasses off, right? And then what I want you to do is take the palms of your hands. I want you to close your eyes, and I want you to press your eyeballs. Okay? And what will happen is initially your eyeballs, you'll see little flashes, and your eyeballs will hurt. And they hurt too much. But after a while, you'll start to see these flickering checkerboards. Okay? Did anybody see them? Like flickering checkerboards, sort of in the center, right? Yes? Right? And I should have brought my LSD goggles today, but I will have them tomorrow. And the thing, I wanted to say the batteries. These are LSD goggles, are goggles you can put on, and they uniformly give you uniform flickering stimulus, okay? And at certain frequencies, your visual field breaks up into these really beautiful geometric patterns, okay? So the first things you just did on your eyes, it hurts, doesn't it? Yeah, now it, these are called deep pressure phosphenes, okay? And the ones you get with flickering light are called flicker phosphenes, or flicker hallucinations. If you want to learn more about these, there's a paper that just came out in, I think, late fall in a journal called eLife, okay, which was with my postdoc and I and a couple of people in Australia on some experimental stuff about manipulations of flicker hallucinations. And then a couple years ago in PLOS Comp Bio, we had a very detailed paper about flicker hallucinations. And I'll sketch a little bit of that maybe today, because I'm not going to talk about it tomorrow because it's too mathematical. But deep pressure phosphenes, there was a fellow by the name of Otto Grusser, okay? Otto Grusser was, he studied pressure in the eyeball because he was interested in things like glaucoma and stuff like that. And what he showed is that when you press on the eyeball, what it does is it blocks any kind of output from the retina back into the brain, okay? That makes sense? So, has anybody ever fallen asleep on their arm in the middle of the night? And then when you wake up, it's like dead. You know, boom. You know, picks up, it's like a piece of meat next to you, okay? So that's essentially what happens when you press your eyeball, is you're preventing any input coming in. You're not cutting the blood off here, you're just pressing on the nerve, okay? Now, of course, it's damaging to do that to your eyeball for a long period of time, and it probably still hurts me, okay? Oh, but if you want to do it really, if you want it to be really magical and amazing, do it in the morning when you wake up after a dream, before you kind of fully open your eyes. Keep them closed and rub your eyes, and you'll see these beautiful geometric multicolored flashes. And then there's a third way to induce this, okay? And that's to take mescaline or LSD or hallucinogens, give rise to visual hallucinations. So I'm not advocating that. That's why I'm advocating pressure or flicker, okay? Okay, so Otto Grusser studied this, and he showed that the eyeball, if you press the eyeball, you're blocking synapses. So I want to think about the state of the visual system, all right? The state of the visual cortex. Visual cortex is back here, and the way to find your visual cortex is to take a book, like a phone book, remember our old phone book, and swing it back and hit the back of your head. Okay, and you'll see stars, okay? That's how you know you hit the visual cortex, okay? Because you're perturbing your brain and in the visual field, and you'll see visual effects, okay? I don't recommend doing it with a heavy book or a brick, okay? But you can do it with a phone book. All right, so the visual cortex, there's been a bunch of experiments by Ken Miller and others, sits in this very balanced state. And Ken even shows null lines between the excitatory and the inhibitory guys. So remember our Wilson-Cowan equations, we have V and U, okay? And the null lines that Ken suggests look like that, okay? So the cortex sits in the inhibitory balanced state, okay? Now, there's tons of random activity going on in your visual system. Even when you close your eyes, okay, there's still some activity. And pressing it gets rid of all that activity. So that activity goes both to the population of inhibition and the population of excitation. Okay? So if you remove the input into the inhibitory neuron, it shifts this null line this direction. Okay? Oh, no, I'm sorry. You remove inputs. Yeah, it shifts it. Which way does it shift it? Right. I want to make it, yeah, it shifts it this way. Okay? Makes it harder for the, yeah. And I better look at my pictures. I don't want to say the wrong thing. Oh, yeah, I forgot to say all this. Okay. Shoot. All right. Oh, we'll get to that in a second. Okay, well, it shifts. Oh, yeah. It shifts both the excitatory and inhibitory null lines, okay? Shifts this guy down and this guy this way. And it can shift this point at different locations on this null line. And it can shift it in a direction that makes it less stable, all right? So that's the hypothesis for deep pressure. Mescaline and other things can also shift this and causes instability. Before I get into thinking about that, I want to tell you about a really phenomenal book that was written in the this really cool book that was written in the 1940s and then revised in the 1960s, okay? And it was Heinrich Klüver, okay? And the name of the book was Mescal and the Mechanisms of Hallucination, okay? And he showed, or he had an appendix in this that talked about what are called the form constants of hallucinations. And it's the kinds of patterns that people see across all cultures in the early stages of visual hallucinations. And these are very simple geometric patterns like spirals and starbursts and like the Wheel of India, things like that. And bullseyes, you know what a bullseye is, right? It's concentric circles and distorted hexagons and things like that, okay? So that's the first thing you have to know, that early stages of visual hallucination give rise to these geometric patterns, okay? Second thing I want to point out is the eyeball, the eye, the visual eye is like polar coordinates, okay? Retina is basically a circle, but the visual cortex is like rectangular coordinates. And there's a mapping of a point which I'll call RE to the I theta. It's a point on the in the visual field, and it goes over to here roughly as the complex logarithm. Log R plus I theta, okay? So what would a bullseye look like in this case? What would a bullseye look like? It's constant along theta, and it's periodic in R. And so you'll get a series of stripes that look like this, okay? Black, white, black, white, black, white in the visual cortex. If you do something like, is it called the Wheel of India? Is that what, how many spokes are there? Huh? 20? 20 what? 24. 24. Ah, that's good. 24 is a antiprime, I believe. Do you guys know what antiprimes are? Okay, a number n is an antiprime if it has more factors than any number any number less than it, okay? So like 6 is antiprime because it has factors 1, 2, 3, and 6. 4 factors. No other number has 4 before that. 24 is an antiprime. 60 is an antiprime. They're beautiful numbers. Lots of people use them. They come up in a lot of cultures. Anyway, so the Wheel of India would have 24 spokes, okay? And what would that look like mapped on the visual? If we imagine them as black, white, like that, how does that map into the visual cortex? That maps as a series of horizontal stripes, okay? And distorted checkerboards turn out, and hexagons turn out to map to regular hexagons and stripes. So basically, Kluver's form constants, spirals, turn out to map to diagonal stripes on the visual cortex. So Kluver's form constants, when viewed from the point of view of the retinocortical transformation, are just geometric, spatially periodic patterns on the cortex. So that suggests that maybe what's going on in the visual cortex is these instabilities are inducing something called pattern-forming instabilities in cortex, okay? So, or symmetry breaking, okay? Now, there was a very famous paper back in the 1950s called something about Turing's paper. What was it called? A model for morphogenesis, or a mathematical model for morphogenesis, or chemical basis for morphogenesis. It was reaction diffusion equations, and I'm going to show you. It's a little bit. This will be a little bit technical, but I hope we can get through it here. I want to study the Wilson-Cowan equations distributed in space, okay? So that's what I'm going to do. I'm going to look at them in space. So let me write down the equations. And to make it easier, I'm going to look at it in one-dimensional space. But two-dimensional space, it's similar. It's just easier to understand in one. I mean, it's easier to just write down in one dimension. Okay? So here's our equations. Du dt. Oh, before I go on, all right, equations that people use, these kinds of models are called neural networks or neural fields. They don't use local coupling. They use long-range coupling. Now, this coupling decays with space, but it's not local. Has anybody here ever played with reaction diffusion equations or anything? Yeah, okay, that's localized coupling. This is non-local coupling. And the reason is that people have experimentally measured that the probability of connections is distance dependent. It decays, but it's not nearest neighbor, okay? So that's the motivation for this. Du dt equals minus u plus, I'm putting the f on the outside. All right, let's unwind what we've written here. Okay? Draw a little picture. Okay? KE is the spread of the E guys to other E guys. Okay? KEI is the spread of these guys to here. Okay? That makes sense? Strength in the spread. KII is, and KEI is this spread, or KIE is this spread. KEI, KIE. Okay? And this is, or you should say, KEE. Okay? And what does this KEE star mean? Okay, it's just the integral over whatever your domain is, if it's the infinite line or the infinite plane, okay? It's just that. Okay? So it's a convolution. Everybody good? And I'm going to assume that okay, that these integrals are integrable and they integrate to some constants, A and M, and they're all positive constants. Now some of these K's might, so typically I'll write, for example, KNM of X is say 1 over square root of pi sigma nm a n m e to the minus there's Gaussian, for example, all right, normalized by the space constant, okay? And then this is the magnitude of these guys. Everybody with me? So what we want to do is study the stability of the equilibriums, the constant steady state. So that's your homogeneous cortex just sitting there. And we want to look at the stability of that. Okay? Does that make sense? Okay? So if we have a uniform state, then then u of x is the same everywhere, and v of x is the same for all x, and these integrals are just a and m, right? And then we get the Wilson-Callan equations. Right, just the usual ones, where these are those integrals. And I've drawn the null lines. I showed you what I thought the null lines should look like, okay? Right? So there's only one equilibrium point, which I'll call u bar v bar, okay? And I'm going to assume that it's asymptotically stable as a solution to this system of equations. So that means if we just solve this equation, this two-dimensional system, and we put it in the computer, and we solved it, we go to spiral in to u bar v bar, okay? So phase plane, things spiral in like that, maybe. Okay, does that make sense? It's an asymptotically stable solution. Everybody with me? But now, we put the network in space. And we want to know whether it's stable to spatial perturbations. Now, as an example, what was the first problem we did after that awful problem in the beginning was binocular rivalry, right? And we found that with respect to symmetric perturbations, it was stable. But if you gave asymmetric perturbations, it became unstable, okay? So that's exactly what we're going to do here. We're assuming that with respect to spatially uniform things, it's stable, and we want to ask what happens. So we linearize this, and we write down, so let f prime of a u bar minus a ei v bar minus theta e be equal to beta e, and f prime of AIEU bar minus AIIV bar minus theta I be equal to beta I. Okay? The slope of these guys. Then the linearized equations are du dt equals minus u plus beta E times KEE u star u minus KEI star v, and tau dv dt equals minus v plus beta I KIE star u minus KII star v. Okay, that's just taking the linearized equations here, writing the derivative of this and evaluating it at the fixed point. All right. Any questions on that? That's just straightforward. Well, okay, it's not straightforward because it's really functional analysis, because I'm not really allowed to just take derivatives. This is something called the Frechet derivative, and it can be made formally. I mean, it's a well-defined thing, okay? But because I only have 30 minutes left, I'm not going to go into Frechet differentiation. In fact, in my PhD thesis, I proved global existence theorems for solutions to the spatial problems and all that sort of stuff on Banach spaces and stuff, because they're really well-behaved equations. All right. How many of you guys do partial differential equations? Do some of you do PDEs? All right. See, my opinion of PDEs is PDEs are bad. Integral equations are good. Why? If you take something that is badly behaved and you integrate, it gets better, right? If you get something that's badly behaved and you differentiate it, it's even worse, right? Right? So you guys are making good things worse. I'm making bad things better. Right? So that's why these are really nice operators, because if you don't work on an infinite domain, they're compact and bounded and everything. They have everything you want to prove global existence solutions to these. Okay? Anyway, that's just my functional analysis hat. So we'll take that back off and we'll put on my math biology hat. We want to study the stability. Okay? Okay, so we reduced this to two linear integral equations. Now comes the fun part. What happens if you take a convolution of e to the I k x? You get e to the I k x back along with the Fourier transform of your kernel, right? Remember that? Cool, right? Okay? So that suggests a solution to this. U of x t, v of x t equal u tilde v tilde e to the lambda t, e to the I don't want to use k because I'll keep calling these guys k. What's a nice qx? Okay? Q is the wave number, okay? Now, if this is finite, if this is like on a ring instead of an infinite line, then these Q's are discrete and depend on the, the length of the ring, and they're 2 pi. 2 pi, if L is the circumference of the ring, then Q are of the form 2 pi n over L, okay? Where n goes from 0 to infinity, okay? So, if we plug that in to here, what do we get? We get lambda u tilde v tilde equals -1 plus beta e k hat of q, k-e-e hat of q. Now what is k hat? K hat of q is the integral minus infinity to infinity k of x e to the minus I qx dx, okay? It's just the Fourier transform of k. Now k is symmetric, so this is actually an even function, so it's really only a function of q squared. For a Gaussian, it's for our Gaussians, it's a n m e to the minus q squared sigma n m squared over 4. Okay? You remember that from Fourier? Some of you nodding, yeah, so you've had Fourier stuff, right? Haven't you had, in India, don't you guys get that like in 5th grade or something? just a joke. Okay? Okay? Notice that when q equals 0, we get our a and m, and as q goes to infinity, it goes to 0, okay? So I'm going to assume that k hat n m is of the form a n m times some common function G of sigma m, oh, that should be squared, Q squared, okay? Assume the same kernel for everybody, different shapes, okay? Or I guess I can just call this K hat, a universal K hat, okay? That'll make it easier when we do the analysis. Okay. So let me, with that in mind, let me write the matrix of linearization. I'll write big psych. Okay? And not beta E. Okay, everybody good with this? This isn't too magical. Oh, incidentally, tau here is the ratio of the time constants of the inhibition to the excitation. Okay, so I don't have to have tau E and tau I. I just rescale time. Just makes for one fewer parameter, -1 minus beta I, AII, KI, or K hat of sigma II squared Q squared over tau. All right, so that's our matrix. Everybody buy that? And how do we determine stability? Well, we look at the determinant and the trace. See, what have I done? I've taken infinite dimensional problem and I've made it where I like it. 2 dimensions, right? Didn't I tell you? 2 dimensions is as good as I can get, all right? So we're going to make a few. So what we want to look at is the determinant and the trace. Okay? All right. So the determinant is this times this minus this times this, okay? So this product, because there's a minus sign and everything else is positive, that's going to give you nice positive stuff, right? But this term may not, okay? This is always negative, but this guy, remember, it's our old friend, star negative plus negative, right? See that every day, right? Every day we've seen that, okay? That's our friend, okay? And we're always going to assume that star is positive because if it were negative, then the phase plane would be down here, remember? We want the phase plane here, so that term has to be positive. Remember, it's positive if the slope of this null line is positive. Okay, remember that? That was exercise on day 1. See, this actually is consistent. So if you remember what I taught you 3 days ago, then this makes sense. If you don't remember it, what can I say? I find my students have a, see, this is nice because you're getting it every day, but we have classes once a week. The time constants I find for students is about 2 days. Okay, they forget everything they've learned 2 days later. Okay, so hopefully, so we want to look at the trace and the determinant of this as a function of Q. Okay, and maybe some other parameter. For example, maybe beta E. Beta E is sort of, remember beta E depended on F prime. So it's kind of, remember what F looks like. So depending on where you are on here, f prime can get bigger or smaller, right? So think of it as moving into this range is making it more excitable. Okay? So maybe we treat beta E as a parameter or something like that. So I don't want to write down all the equations for what the trace looks like, but let's plot first the determinant as a function of Q. Now, what do we know when Q equals 0? What's the determinant when Q equals 0? What did I say earlier? I said that that equilibrium point in the homogeneous case, the uniform case, was stable with respect to uniform perturbations. So that's Q equals 0. So that means the determinant has to be positive, right? So the determinant is positive here. Now, let's look at what happens as Q goes to infinity. Okay? Q goes to infinity, this term goes away, this term goes away, this term goes away, this term goes away, right? Because all those K's go to 0, and we're left with -1 over tau, and 0. What's the determinant? 1 over tau. It's positive, right? So, that picture. So what we're looking for is we would like to see maybe something like this. These all have to go the same way. Oh, yeah. What this would be, say, beta E greater than beta E, or beta E greater than beta E star. Beta E equal beta E star. Beta E less than beta E, or greater than beta E star. Oh, this is less than beta E star, equal greater than beta E star. Okay, I'm changing the excitability of this either by pressing on my eyeballs or dropping acid or something like that, okay? What's happening is as I do that, I'm getting a band of spatial perturbations that grow, okay? Do you see that? And if this is on a finite domain, instead of a continuous line, there's a bunch of dots, okay? So that would be scenario 1. What about the trace? We could also have a situation with the trace. I'll draw trace over here. Now, here's the trace. And we know it's negative when Q equals 0, right? And we know as Q goes to infinity, it's also negative. So maybe we have something that looks like this. That's another possibility as we change the excitability, right? So this, suppose that we had this, but the trace remained negative the whole way, okay, for all Q. Then this means the determinant's going to 0. We have a 0 eigenvalue. And that suggests we'll get stationary patterns, patterns that don't change in time, because there's 0 eigenvalue, all right? Up here, suppose the determinant remained positive all through all Q, but the trace went bad, okay? What happens then? What do you expect to happen then? Well, then, you expect to see Hopf bifurcations, but they're more complicated because they have a spatial component. So you'll get solutions that look like e to the I omega t plus IQX, e to the I omega t minus IQX, and so on. Okay? In 2 dimensions, 2 spatial dimensions, because this network is homogeneous, I mean, because it's isotropic, the kernels are completely symmetric. It means that if that q squared is alpha squared plus beta squared, or alpha, say qx squared plus qy squared, and this perturbations are e to the I qx. They only depend on the magnitudes of qx and qy. So there can be infinitely many spatial perturbations in 2 dimensions. So usually what you do is you work on a lattice, right? Turns out that in this particular case, let me see how much I say here. All right. So in 2 dimensions, 2 spatial dimensions, let me just do the 2 spatial dimensions first, because I want to write down a little bit of cool math. Okay? In 2 space dimensions, okay? Suppose that the determinant goes negative, but the trace remains negative for all q, okay? And let's work on a square lattice. Then e to the I qx, e to the I qy are the 2 independent eigenfunctions. One represents vertical stripes, one represents horizontal stripes. Does that make sense? And it turns out that you can use the miracles of modern bifurcation theory to write that uv is equal to u tilde v tilde plus z complex conjugates. Okay. You write down solutions like this, all right? Where u1, v1 is the eigenvector of this matrix at the critical value of q, corresponding to the 0 eigenvalue. Okay? Remember u bar, this shouldn't be u bar tilde, this is u bar. U bar, v bar is just the equilibrium point. And z satisfies the following differential equations. Okay. So these are called the normal forms, and you can compute them in lots of different techniques. You can compute them, these coefficients explicitly, or you can infer what they look like by symmetry arguments, okay? For that, you should talk to Amit. You worked with Marty long enough that you probably know these things, or not, maybe not. Any case, these equations are the amplitude equations, complex amplitude equations for the behavior of this system, okay? And A and B are both real, all right? So, in the last 11 minutes, I guess I won't talk about the temporal case because it's too complicated. So I'll just talk about this, okay? Because it's kind of cool. All right, so let's see where we get with this, all right? Since A and B are real, okay, I'm going to let Z equal R e to the I theta and W equal S e to the I psi. And I'm going to get R dot equals R, and let me just call this thing P, parameter P. So if P is negative, we're below criticality. If P is positive, we're above, okay? Okay? Theta doesn't show up at all. Basically, you get something like that. Doesn't matter. They can be anything because all these things, anything can be translated in 2 dimensions. Okay? So this is really cool because now, what are the equilibrium points to this? Let's suppose P is greater than 0 and A and B are greater than 0, okay? I put the minus signs there to make the algebra, so I didn't have to have all these stinking minus signs, okay? One solution is 0, 0. That would be pretty boring. That's not a pattern. And if P is positive, it should be clear that it's unstable. R dot equals PR, okay? Another possibility is square root of P over A, 0, and 0 square root of P over A. So that would be S equals 0, R not 0, or R equals 0, S not 0. See that? And then the final case is square root of P over A plus B. Okay? So let's unwind this. What do these correspond to? This corresponds to no pattern. This corresponds to vertical stripes. So this is vertical stripes, horizontal stripes. What's this? What's that correspond to? Huh? No, it's not. It's because it's the sum of these two guys equally. It's checkerboards. Yeah, no, you don't. You know, I can see why you might think that, but think of adding horizontal stripes plus vertical stripes, you get checkerboards. Yeah, that was a good guess. This is checkerboards. All right, homework. Homework, yet another homework. You guys got a lot of homework to do. I'm not grading it. Prane's going to grade them. Homework. If A bigger than B, then checks are stable. If A less than B, then stripes are stable. Before I go on, I have a question for the organizers of the conference next week. Are you doing ecology modeling at all or not? Are you going to do competitive competition at all?
You probably just mentioned
Huh?
one day for complete ecology.
Because this is a competitive system. If you multiply this by R, multiply that by S, then it becomes something to the form R dot equals 2RP minus AR minus BS, and similarly, that's a standard competitive system. And if B is bigger than A, it means that you get competed on harder than you are on your own self. And so the only state that exists that's stable is one guy winning and the other guy off, okay? Whereas if B is small compared to A, then you can have the coexistence state. This is classic competitive ecology model. But you get it here. So that's where this comes from. Okay? So what this tells us is that depending on the parameters of your model, you're going to either see stripes, either horizontal stripes or vertical stripes, or checkerboards, but you shouldn't see both because both of them can't be simultaneously stable. Okay? Now, what happens in the case of the Hopf bifurcation in 2D is much more complicated because instead of having a two-dimensional null space, you also have e to the I omega t here, and you have the two complex conjugates of that. So you have a four-dimensional space, and you can get really cool stuff. You can get flickering checkerboards. You can get traveling wave stripes, you can get traveling checkerboards, okay? All this stuff, it's really cool, okay? So if you want to see some of those patterns, you can, I wrote a chapter in the book with Zach Kilpatrick and Stefano Foyos, but there's also, actually I wrote a paper many years ago called Neural Networks Spatio-Temporal Pattern Forming Systems. I believe it's like 1996. And I think it has pictures of some of these things, okay, in 2D. Okay, so I think that concludes everything I want to say. I mean, there's many other things I could say, but I'm tired. You're probably sick of me. And there's only 3 minutes and 52 seconds left. Maybe I should wait for another 30 seconds so I could stop at pi. But this is a math thing. So anyway, this is sort of the basis for, this can be used to lots of other things. These ideas are universal in all pattern formation. Okay? Everything that people have studied doing pattern formation, reaction diffusion equations, George Oster did a whole series of things that involve mechanical, chemical coupling. There's all sorts of things that involve other kinds of spatial coupling. But whenever you have coupling interactions that are isotropic, they don't care what direction you're going, and translation invariant, you're always going to get this same idea of spontaneous checkerboards and things like that. Now, in more complicated domains, for example, circular or a disk-like domain or a sphere, suppose that you had that instead of an infinite plane, then you'll get things that are related to the eigenfunctions, you know, the Bessel functions with the spherical harmonics, but you'll still get these same geometric patterns, okay? You know what Bessel functions look like, right? The normal modes on that. And this linear analysis selects the wavelength, but nonlinear analysis is needed to select the pattern from an infinite number. So if you look at this, depending on what I choose for W, if I just take the real part here and change this to cosine QX and, okay? Depending on what I choose for RNS, there's infinitely many patterns that vary from stripes to checkerboards, right? But the nonlinear stuff smashes that all down to only 3 possibilities, okay? And that's what a lot of people that do this work, or in the old days, they don't anymore, but in the old days, they missed this. There were questions about why are there stripes? Why are there spots? Is it because there's something about the linearization? The answer is you cannot tell from the non-linearization. You need to use the nonlinearities. And that's what makes it interesting, makes it hard. All right.